Let's now start on lecture 17. We're going to continue looking at high-level language translate into assembly language. How do we do the translation? I will post homework for shortly, and it's due next Thursday. We talked about global variables. They are static. They are allocated in data segment. Other variables, they are dynamic, and they are allocated on stack. We use stack frame for each function, and in the frame we have the necessary information for the function to perform its operations. We have saved variables within the function. We have local variables for that function starting at EBP minus 4. We save EBP and EIP for return, and also we have function arguments passed into which start at EBP plus 8. This is the stack frame we showed you earlier. We have this stack. This is the higher address, and EBP is where we can use as a marker to find all the necessary parameters or variables, and ESP is the current top of stack. EBP or BP is used to reference data within the frame. And we talk about this example where we have symbols defined to represent the starting address of each variable, and use these symbols and EBP, we can find their locations. To access array, we need to have the base address of array and the offset into the array. The base address typically is defined as a symbol. For example, we had earlier in the previous slide, we have underscore capital X $sign. That's a symbol representing the starting address or the base address of array. For offset into array, we can use the index to calculate that offset. For example, in our case, we have integer array. And each integer is a 32-bit number which takes 4 bytes. So if we refer to the second element of array X, remember we're counting from 0, so the offset will be this index times 4, that is the size of each element. In our case, that's 4 bytes per element. So the offset is going to be 8 bytes into the array X. In some instruction set architecture, you need to explicitly calculate this address. So you spend additional instruction to do the multiplication to get the actual address. In x86, we have this scaled addressing mode where multiplication is done in the memory access instruction. For example, if we want access for our code, we want to assign to the value of the ith element of array X, we assign twice of the index. The way we do it is by using the following 4 instructions. First, we load the value of index, the variable I, into EAX. That's this move instruction. Remember, underscore I is the offset, and that's offset to the EBP pointer. So this will provide you the memory address to variable I. We're going to copy that into EAX. Then we do shift to the left for 1 bit. That's the same as multiply with 2. And it's much easier to do shift than doing multiplication from the microprocessor point of view. So EAX now has the twice value of original value of I. Then the third instruction is to do another loading the index to ECX. This underscore I $ bracket BP, this again is the address of variable I. So we're going to use that, and we do memory access. We're going to load that index into ECX. So we're actually finding out what is this number, what is the index. The next instruction is to do a data transfer. We copy the shifted value. Okay, this is twice of index of I, and then we use I. This is I, the index, times 4, and then add it on top of this underscore capital X $EBP. If we just look at this underscore capital X $EBP, this gives you the starting address or the base address of the array. Then we're going to add that to this I times 4. This 4 is because of every element takes 4 bytes. So this altogether gives you the offset to that ith element. And we're going to copy the value into that location. Is this clear? Okay, what is your question? Do you follow this first instruction? Okay, so what does this instruction do? This first instruction. The first instruction, let's stay on the first instruction. First instruction is copying an integer from memory to EAX. What is that integer? That's I, that's variable I. And then the second instruction is that value times 2. Because when you shift to the left by 1 bit, that's the same as you multiply number by 2.
Sorry, it's variable I because that underscore I $saying the offset of
Yeah.
Which we said, did we define that?
We define underscore I $.
Okay.
And we use that as the offset to EBP. So this essentially take this defined value, add that to EBP, and that gives you the offset to the actual variable I. And we do the same because we again need that value in ECX for doing this scaling. We put it to ECX. Now this ECX has the value of I, variable I. We multiply that value by 4 because each element takes 4 bytes in the array. These underscore capital X $EBP, this gives you the base address of the array. So if we look at this diagram, that will tell you for this is X. For array X, where is that? This is array X. The base address of the array. The next one is X1 and so on. So this, in our example, this underscore capital X $EBP, that tells you base address of the array. Then we're going to do this ECX multiply with 4. That's because we're going to find out I times 4 for the scaling. We'll add this with this. That will tell me where is my ith element of X. And we assign value that is I times 2. That's exactly this line of C code we're trying to implement. This one? This one, this example, we're talking about element 2 in X. And this is the index. This 4 is because each element takes 4 bytes. So what is your question? Size of the... This times 4 is this 4. Don't confuse this I times 2 with I times 4. This I times 2 is the value we want to put it in, whereas this I times 4 is the location of that variable. Conditional statements, if then else statements typically take form similar to the following. You have code to evaluate condition first, and then you have conditional jump to else if the condition is not true. If the condition is true, you're going to execute some code, and then you're going to take unconditional jump to the end. This else part takes care of these operations if the condition is false. We always start with some code to evaluate condition. And this is required a conditional branch, and we must add a label to the branch to else statement, like here. You need to have some label here because for this conditional jump, you need to take the microprocessor to this point. Once statement for if condition is complete, jump will pass else statement. This JMP will jump past this else statement to the end. You don't have to use ELSE or AND. You can use any label that makes sense. And you should use a more meaningful one than else and AND here. Recall that this is the C statements inside the inner loop. We're going to check whether J is less than 5 or not. If J is less than 5, we're going to assign this x of I plus J to J's element of I, Y. Else, we're going to assign the ith element of x minus J to the J's element of array Y. So this is the typical if then else statement in C or in any high-level language programs. And on the right, these are the instructions we will need to implement that if then else in assembly language in x86. So we see we have a condition or comparison instruction here to check whether the condition is true or not. And this typically done is by using CMP. In our case, we compare this variable J with immediate value 5. So this is doing J minus 5. If it is greater than, if J is greater than 5 or equal to 5, we will jump to there's a short label ln2 at main. This is some label here, so we're going to look at where it is. It's actually here. So this is the else part. Okay, because we're checking J is greater than or equal, so that's this else part. So in this else part, what we're going to do is we're going to first load we're going to find out the value of ith element of array X, and then we're going to subtract J from it, and we're going to assign that value to J, the element of Y. That's what we're going to do for the else part. That one line will actually need these 5 lines of assembly code to implement, because we need to find the actual value of variable I. That's the index. This is the address of I, variable I. Then we're going to copy the value from that memory location into EAX. And then we're going to use that index to scale that by 4 so that we can find the location of the ith element of X. Remember, this is the address. Okay, this whole thing is the address, and we use default pointer to say that, oh, I want to go to that address. I want to load the value into ECX. So by this time, once this instruction is completed, this ith element of X, the value of it, is going to be loaded into ECX. Exactly, that's double word. We use default pointer to say that we're going to take an integer, which is 32-bit. The next instruction, this one, is going to subtract. This is the variable J. Okay, this is the address of variable J. So we're going to subtract the value of J from ECX. So this is to do this subtraction operation. By this line, by this subtraction instruction, we have completed this assignment, the right side of this assignment. Okay. After this subtraction instruction is completed, ECX will have this difference. The next one, we will use the address of variable J, and then we're going to load the value of J to EDX. Why would we do that? Because the left side assignment is, again, an element of array, so we need to use the index to scale and to find the offset into the array. That's why you see here this EDX times 4, that's actually J times 4. That's how far we should go into the array starting from its base address. Good. So this is the else part. The then part is similar. So we're going to do this addition instead of subtraction. Everything else the same. So that was the if then else. The next component for high-level language often used is loop. Loop essentially has 3 parts. We're going to first initialize loop index, and then we're going to check the boundary condition. Similar to if then else, but simpler. If condition is false, we're going to end the loop. So we'll branch to a label at the instruction after the loop. It's usually done at the starting of the loop, since no iteration should occur unless the condition is true. And the end of loop will contain the jump back to the beginning. So that's what we do in the loop iteration. And one important thing we also need to do is to increment or decrement the loop index, depending on how you design the loop. Let's look at this example. This is the inner loop. We have a loop counter. We use J, variable J as the counter. And we increment it every time. And the condition is J is less than 10. Let's see in assembly language how we implement this loop. We will initialize the counter. Now this _j $EBP comes back again, your good friend. This is the address of variable j, so we're putting 0 into that memory location. This is what we do for j equals 0, or assign 0 to j. This instruction is doing that. Next one is JMP short ln5 at main. This is a label. This is a label generated by the compiler. So we get to this point. You see we do a comparison. Because for this C statement, we'll have to first check this condition. If the condition is false at the very beginning, we'll do no iterations at all. We'll do nothing inside this loop. We compare the value of j, okay, and this variable j is in memory, and we have this address. This is the j's address. So we compare this memory operand with the immediate value 10. So we do a subtraction. So this j minus 10. That's what we do here. JGE will jump if j is greater than or equal to 10. So that's the end of the loop. We should not do anything else if the condition is not true at the very beginning. So if that's the case, we'll jump to ln3 at main. So that's basically the finish point of the whole loop. Well, in our case, typically that's not true at the beginning, right? Because the initial value is 0, so this will not be true. So we will execute the following instructions here. That's where the main loop body is at. So these are the instructions in the loop iteration. You can have plenty of them here. After they are done, we'll do jump short ln4 main. Okay, we'll jump back to here. What we're doing here, we're actually doing this increment. Remember, we have to do this in every loop iteration. So we do that. We load the value of variable j to EAX. We add that by 1. And the destination is EAX. So now EAX has the incremented value. And we store that value back to j. Because always j will be updated. J is in memory, so we need to update that. And then we're going to do the comparison again to decide whether we should continue to the next loop iteration or not. Okay, then if that's not true, if j is not greater than or equal to 10, that means we're going to do this loop iteration again. Then we do this increment again, then we do compare, and so on. Yes, j is a 32-bit integer. That's what we used in the C program. If you remember, we have the C code, we have integer I, comma j. So both variable I and j are 32-bit integers. Well, D word is referring to 32-bit values. Yeah. Word is for 16-bit. And you can have byte, that's for 8-bit.